Donc, bienvenue à cette nouvelle séance du séminaire sur le calcul sécurisé. Et donc aujourd'hui, nous avons le plaisir d'accueillir Michele et Orrù. Donc Michele est chargé de recherche au CNRS, exerce au laboratoire IRIF de l'université Paris-Cité. Et il a fait son début de carrière à l'université de Californie à Berkeley. Donc c'est un spécialiste alors à la fois donc de la théorie et des principes des preuves zero knowledge et autres constructions cryptographiques, mais aussi de leurs applications pour l'anonymat et le respect de la vie privée sur Internet. Et il a fait donc à la fois des contributions théoriques remarquables, mais aussi par exemple, développer une plateforme sécurisée, un logiciel libre pour les lanceurs d'alerte, pour les whistleblowers, et il participe actuellement à des efforts de standardisation aussi autour des protocoles Sigma qu'on a vu et de Sigma non interactif qu'on a vu ce matin en cours. Et voilà, donc je pense que c'était vraiment la bonne personne pour nous parler davantage de ces applications des preuves zero knowledge. Et même si il parle en fait très bien français, il préfère faire l'exposé en anglais. J'espère que ce ne sera pas un problème. Et de toute façon, vous pouvez poser vos questions en français, il n'y a aucun souci. Merci à toi Michele.
Merci. Je vais essayer de faire un peu de franglais, mais tu nous comptes que Zero Knowledge Proof, ça va être pas facile à traduire tout le temps en français. Je vais passer en anglais assez rapidement. Je crois que le message de base de cette intervention, c'est qu'il est possible d'utiliser les frameworks que Xavier a donné tout à l'heure pour construire des outils qui aident à fournir de l'authentification et offrir en même temps l'anonymat. Et donc, mon but avec cet exposé, c'est de vous donner un peu plus de contexte et réitérer sur des concepts sur les preuves zero knowledge. Ensuite, passer aux anonymous credentials et terminer par confidential transactions. Comment il est possible de faire, comment on peut faire des paiements de façon anonyme. Et voilà, donc on démarre avec les preuves. One of the things that's interesting about zero knowledge proofs, c'est que it's that they started as a generalization of the NP class. La classe des preuves en maths, c'est la classe NP pour les infos. A language, we say that it's an NP if it can be efficiently decided by a verifier. If every instance in the language can be checked with the help of an auxiliary input called the witness. And so PT means polynomial time. The verifier will accept any witness that with the help of a witness will be able to accept any instance in the language, every word in the language. It will reject any instance that is not for whatever string you give me. And as we will talk most of the time about NP relations, I think it's important to stop for a second and also think about what this means. We will study relations associated to a language. It will be useful for us to think about pairs of instance and witnesses, and that's what we did already in the last lecture, where we've been mostly looking at groups that are cyclic of order P, and that are generated by this generator P, and so we're studying essentially the set of this element that's like added to itself many times. I'm using here additive notation instead of multiplicative one because that's the one that we use most of the time in elliptic curves. And the relation that we most often will think about or that will reduce problems to is the discrete logarithm relation, which is the where the instance is an element in the group and the discrete logarithm, it's the witness. And we know that it's easy to check if, given like the little integer, whether the element is really in the group, for instance. But most of the languages that we will deal with are languages of the form public key, of which I know a secret key. And one of the things that we say in proof systems, and that specifically is relevant for NP relations, is that la preuve plus simple, c'est juste envoyer les témoins. It's the simplest proof is just sending the witness. And this is a way also of saying, like, we're really trying to generalize this notion. And you will be surprised how often this is also used in real-world systems. I was just in this hotel in Denmark just before coming here, and like also there you have these authentication systems. And these authentication systems essentially boil down to writing or issuing, that's the language that we use, a user identity or a key that sort of represents your entity in the system. And this sort of card allows you to unlock your room by essentially sending the private key to the door. But the way in which it's done is literally just send the private key, which means that also anybody that is able to emulate and create a functioning clone just can send the same secret key again and log in at the same time, right? Like there is nothing special about that particular system. So ideally what we want to do is something a little bit better than this. We want to keep some of the information private when we are authenticating. And hopefully also this convinces us that, we're dealing with something that is much wider than NP. In fact, one of the fundamental proofs in this area is that the space of interactive proofs is equal to P space. And so around 85, Goldwasser, Michele, Rakov, and Babai in parallel went to sort of generalize this notion by adding two components, interaction and randomness. And one of the things that we saw even earlier is that randomness can really help in a lot of algorithms, like polynomial identity testing is something that's really hard to do efficiently without randomness, but as soon as you have randomness, this becomes trivial. And so we say now that a language is has an interactive proof if there is a verifier, and not that now the verifier is interactive and it's probabilistic polynomial time, they can check membership, but now it does not talk to a string, it talks to another machine, an interactive Turing machine that is computationally unbounded. And if this element is not in the language, then no matter how long any prover will spend trying to convince me, I will not accept this string. I will always reject. Or at least I will reject with a sufficiently high probability. Because we're dealing with randomized algorithms, so all these properties are now have this like sort of ugly probability in it, but that's how we do things. What's even more interesting is that, so, like you have these two machines, they are talking, and what's interesting here is that pretty much you can reduce these protocols to the verifier is always just sending a random string, and at the end is checking an equation. That's why we call this class of protocols, like we generally consider or focus on protocols that are public coin. Because any interactive proof, I can reduce it to the verifier just sending random data, and at the end checking something. That's the case that you already saw with Schnorr, which has this sort of is a special case of Sigma protocols, where you have like these three messages, the commitment, the challenge, and the response, that have this structure, which are then verified by checking the same equation for the response, but in the group. And again, here, the protocol is public coin because the challenge is essentially a random number that's being sent to the prover. And this is an interactive proof. And it is an interactive proof that has very strong soundness properties. The soundness that is satisfied that you showed earlier, and that I just want to summarize once again, is that if you give me two valid proofs, if you are such a good prover, you will be able to convince me with two different challenges. You know what they say, fool me twice. And the idea here is that if you are able to give me two valid transcripts with different challenges but the same commitment, I am able to recover the witness. And the way to do it is essentially inverting a linear system. And by the way, this is exactly the way in which we write things in practice. This is an extract of code. It is literally pretty much the Schnorr protocol, so this Sigma protocol, where we kind of want to abstract away the Fiat-Shamir transformation and just talk about interactive proof. And even in the theory, despite, we try to think about applied system, we keep on thinking about prover and verifiers in this way. This protocol has another very important property, which is that it is zero knowledge. The zero knowledge property is a way of asking ourselves like how much information is being leaked in a proof. In math, we have also these ideas of like proof that can be built in a non-constructive way. And in computer science, the way that we think about like how do you say that you're not leaking information is by saying that I can reproduce every distribution, every out distribution without knowing the secret. What is the distribution in this interaction? Well, it's the set of prover and verifier messages. Is the view of the prover and the verifier invoked on that input. And we're trying to say that it's indistinguishable by whatever can be produced by an algorithm that is efficient and that only knows the instance. In the case of Schnorr, this is sort of immediate because we are essentially dealing with random data that satisfies a linear equation. And providing such a simulator is really easy. And the crucial property here is that we're playing with the order in which elements are being sent. The sort of the core property here is that the prover can be even computationally bounded, but it's the fact that I can challenge it on data and you don't know where I'm going to query you is what's giving this power. And that's what the simulator is exploiting in order to produce simulated transcripts. Why do we think about, so also one other parenthesis, in the case of Schnorr, we can simulate, yes, but we can simulate as long as we know the distribution of the challenge. That's why it's called honest verifier zero knowledge, in that, sure, we know the distribution about these proven verifier messages as long as we know the distribution of this challenge. And the reason why we generally focus on even this weak notion of zero knowledge, honest verifier zero knowledge, is that at the end of the day, we're not really talking about a verifier. In application of anonymity, we might not even know who we are talking to. We generally do what we call the Fiat-Shamir transformation, which allows to turn a public coin interactive proof into a non-interactive argument by means of a cryptographic hash function that I'm calling here f. And roughly speaking, the way in which it works, that we also saw earlier, is by replacing the verifier interaction with the interaction with a random oracle and then producing a random non-interactive argument string. And the exact way in which this oracle is being queried, what are the inputs and how the string has been constructed at the end, has been actually defined over and over again in the last 40 years. So today, Fiat-Shamir is more of an umbrella term for multiple transformation than a single well-defined one. The way in which I would like you to think about this for now, the way that we study in papers and that we know the security of, and that I'm going to call the canonical Fiat-Shamir transformation, asks that the random oracle is invoked on the instance and all of the prover messages that were sent so far. And the non-interactive argument string at this point is only the prover messages, the sequence of them. The verifier on the other end can parse the string by reading the prover messages and then reconstruct the verifier messages by querying the random oracle and then output the decision bit of the interactive verifier, which again, as I said, is only like verifying an equation after sending all this random data. And in the case of multi-round protocols, so when we're talking a lot of times, so not only sigma protocols, we're doing the same thing, except that we have one oracle per each round. And at each round, I'm assuming that there is this magic function, this random oracle, that takes as input an instance, all of the prover messages up to the ith message, and that outputs a uniformly distributed verifier message in the ith verifier message space. Now, there is some difference between the security in the interactive proof and whenever I start talking to a random oracle, right? Because I'm not interacting only once. An adversary can try to attack across many different sessions and try to obtain many different messages. He can literally stop at any round and try many prover messages and get many verifier challenges at blocking the execution at any round. And then we call this class of attacks state restoration attacks. And that's why when we study the security of this Fiat-Shamir transformation, we don't even think about like the classical soundness definition. We study generally something called state restoration soundness that deals exactly with the specific class of attacks. So an adversary that can stop the verifier and ask for many prover messages and get many different verifier messages at any round. And from here, we know how to build reductions to sigma protocols, so that, for instance, which satisfy special soundness, or round-by-round soundness, which is what is used more by modern snarks, like snarks that were mentioned earlier. And in fact, in practice, it's not like we have these magic random oracles that go from like prover space to verifier space. In practice, what people have been building and standardizing are hash functions that are of fixed length over a specific domain. And the exact way in which you reduce to these like little component is something that we've been playing for quite a while now. And also proving this reduction is something that we're still ongoing. Literally, I literally have been writing a paper about this, so it's still something that where there is a lot to say. And most importantly, there is also security loss in mapping from these sort of functions that we would like to have in the theory and the ones that we have in practice with acts of a fixed size. One very simple way to think about this is that at some point you might have collisions in all these little codes, and so you need to deal about them. And in practice, really, we have essentially two tools like SHA-256 or Blake2, which map twice the block size into one block size. These are compression functions, and permutation functions, which are the thing that is more up and coming these days. That is at the base of SHA-3, and essentially acts as a random permutation. And there is an entire field of cryptography, of symmetric cryptography, that's built around building symmetric tools from random permutations. In our case, for the rest of the talk, I will essentially consider this idealized function, so random oracles. But in practice, that's what we use. And this is a leap of faith that I'm making, right? I'm saying this is an oracle, and when I instantiate, this thing is still secure. And as Xavier previously mentioned, we know this is not true. There is an inherent difference between, giving a machine access to an oracle and giving it as input a circuit. We call this diagonalization. We called it sometimes it's used for things also in PL, like Rice theorem. But yeah, it's not true. But for practical reasons, it's a valid heuristic that works. So we know how to build proof systems, in this case, that are insecure for any instantiations of the hash function. But for most of the things that we use, it's fine. There is an entire other branch of literature that is studying how to do this securely. And roughly speaking, the way in which it works is that you need to have some strong statistical guarantees on the proof system, and then build something called a hash function that has a property called correlation intractability. This is a very long line of literature. I'm not going to talk about it. The main reason is that it's inefficient, and as of now, it's mostly a theoretical object of theoretical interest. So what we end up with as you get down the trenches of practice and of the real world is another definition of knowledge of interactive proof, which is arguments. And note that what we're interested here is also how can we make this efficient using cryptography. The idea is that now we're interested, in a verifier, sure, that is probabilistic and runs that is non-interactive, most of all, sorry. But also a prover that is efficient. We don't care about provers that run in exponential time because we want to get a proof, in a reasonable amount of time. But also we're thinking about random oracles. So we have these machines that can talk to oracles and then produce outputs. And finally, we also do not care about adversaries that are computationally bounded. When we think about hypotheses like the discrete logarithm, an adversary that is computationally bounded will obviously be able to solve it. What we're trying to say here is the adversary will not be able to solve this problem in a reasonable amount of time. And what is interesting about all of this is that, first of all, the reason why we have the prover that are computationally bounded is what makes us call them arguments rather than proofs. But also the addition of this computational time bound allows us to insert cryptography. And inserting cryptography allows us to have things that we wouldn't think are possible. We can literally verify and check execution faster than it would be to recompute it. And how is it possible? How can you do it? Right? In general, we have a big hierarchy of theorems in complexity theory that tells us that in general there is no way of reducing time and space of an algorithm. And doing this, the magic of this is that we're using some cryptography in order to leverage that, and we have some sort of computational soundness guarantees. That's also something that was explained in the previous talk, but it's like one of the fundamental results in the area is really you can check things faster than re-executing them, thanks to cryptography. And the cryptography that we're using is not public key cryptography necessarily. We can base all of these only on one-way function. And it's really mind-blowing, at least to me, that you can base such complex cryptographic primitives like proving knowledge of an arbitrary circuit on simple functions like hash functions. That's all you need, in theory at least, and also in practice in most modern systems. And the way in which I want to show you like how can this be done, how can you prove things faster, or how can you at least have smaller proofs, is starting with Maurer proofs that we saw earlier. In Maurer proofs, you're proving the preimage of a morphism, that is like mapping elements from scalars into the group. And so you have this relation that I'm showing here, where I'm denoting the morphism as a matrix M. And like you're essentially doing a matrix vector product. You need to make sure that the dimension maxes, etc. But what's important is that with Maurer proofs, you can sort of leverage it to prove pretty much any NP computation, any circuit, and just using it as a building block. And the proofs are very similar. They are sigma protocol, and they maintain the same structure that I showed earlier. But the key for reaching these short proofs, or the key for achieving these faster verification, is instead of sending like the wall response in here, as you would, why you don't want to send it? Because it has the size of the witness. It has the same size of the scalar. If the scalar has n elements, this vector has n elements. And instead of sending this element and then checking the mapping under M for this linear function, which again creates a problem for size, what you can do is you do not send it, and instead you look at this matrix vector product, and you act in the same way that you would think when you're computing an FFT. You split the matrix in two, you split the vector in two, and you consider the products of them separately. And now, instead of like thinking about one big matrix times one big product, you think about two smaller elements of size n divided by 2. And then you do what cryptographers like to do all the time, taking random linear combinations of them. And so you end up, you can think, and actually you can really build protocols that were essentially act recursively by splitting the instance from size n to n divided by 2, and then recurse on that. So we end up with a base case where you just send the response. Sure, it has constant size at this point. And in the recursive case, instead, you send another challenge, and then you use it for folding the witness. By folding here, I mean you take the random linear combination of the two. Now, you can build another instance, but it's not like m prime times r prime multiplied together give me the initial result, but give me something closer. I just need to think about the cross products, A and B, and then I can recursively check this equation instead. Again, the idea for moving from what you saw earlier, like Maurer proofs, into something that has like log size is by split, fold, and then recurse on that. And at each round, you would send the sort of intermediate the cross products. And so the efficiency of this system, what is it? At every step, I'm reducing the vectors over which I'm operating by factor 2. So overall, the prover will run in linear time. And the proof size is logarithmic, right? Because at each round, I'm sending log elements. I'm increasing the number of rounds, yes, but at each round, I'm sending a constant number of elements. And what's important in this specific example that I showed is that this is still secure as long as I maintain some sort of like binding properties over these vectors when I fold them. That's where the argument part kicks in. And the way in which we prove soundness of these systems is still by performing some type of extraction, except that while before I was like looking at solving a linear system with 2 unknowns and 2 variables that is non-trivial, here I will have to think about a linear system that has a larger number of variables and it's operating like essentially on a van der Monde matrix. Because the folding happens over a degree 2 polynomial, right? Like if you look over here, I end up with, In here, the thing that I'm checking recursively, so the verification equation is operating over a degree 2 polynomial. So I need at least as many as the degree in order, as many equations as the degree in order to solve it. And so what I want to stress is that this is a pattern that we use over and over again. It's not something that's special about discrete logarithm groups. It's not special about the scheme that I gave. It is possible to study these protocols independently even from the discrete logarithm, assuming that you're essentially sending oracle messages out. So not computing these sort of matrix vector product in the group, but rather, for instance, sending Merkle trees of them or sending something else. And there is an entire field of the theory of cryptography that is studying these systems in what is called the PCP or the IOP model, where you're sending oracles and you're allowed to perform some operations on them. This protocol has also another name that has been fundamental in the theory of interactive proofs, and it's called the sum check protocol. What I'm showing you is like essentially an application of it. And now that we have this system, and as we saw earlier, but I also, as I mentioned just a second ago, you can build a lot from it. You can build circuits. And all that I'm building now is essentially examples of how to use this system. And the system, as we just saw, can be like even faster and more efficient than just sending the answer, the secret keys all the time, right? So what we're going to do now is see two pretty toys, two like improved means for unimproved ends, for authentication and anonymity, for payments and anonymous identification. I'm starting with anonymous identification. And the example that I wanted to give is the example of whistleblowing, where you have a user, and the user wants to report some information or some misbehavior that's in the public interest, but wants to do so anonymously by getting in touch with, for instance, some journalists. And the way in which design these systems today is by having them talk through a server that is end-to-end encrypting the data and allowing them to share messages. But again, the whistleblower wants to be anonymous, so there you go. You have authentication and you have anonymity. And in fact, the way that these systems are built today are such that the anonymity is with respect to any of the users. It's not even about like, is this user talking to a journalist, but I don't know which user it is. It's really like a user is getting data from the server, I don't know who. This brings me to like, what does it mean to have anonymity? And one of the core concepts that we have in our field is this notion of the anonymity set. How many users could have performed the same transaction as you? How big is this set? How big is the herd inside which you're hiding? And in the theory, this takes a lot of names. It can take the name of blindness, unlinkability, anonymity. But for now, for the rest of this talk, also because we just saw zero knowledge, I want you to think about the view of the server is indistinguishable and can be simulated by the simulator. And now, because each user is indistinguishable from the simulator, I can kind of hope that all of them are indistinguishable as a group. And all of the authentication protocols that I know of, any authentication protocol, has two phases. An issuance phase where I give you the credential, and a presentation phase where I use the credential to access something or to perform some operation. Think about the hotel case, right? I check in, I get the card, and then I go back and I present the credential to the door and I want to get in. Think about HTTPS. I build a certificate signing request from the certificate authority and then I present it to the user. Or think about a VPN. I buy some credit, I do the KYC, and then I want to use it. And anonymous credentials are essentially a way of splitting these two transactions, these two protocols in such a way that you cannot tell whether the holder, the user that was first asking for the credential and then using it is the same. And in fact, we can build credentials where I can give you a signature, I can give you like a credential once, and you can perform a lot of operations after it. And these have been used a lot in both big tech as well as large open source projects for public good in recent years. They do not only allow to protect users, they also give good privacy stories, or they diminish liabilities for companies. And as we move forward with all of these, like there have been a ton of standardization efforts for these primitives, or better, application of these primitives in the last years. This is a list only within the IETF, but there are other standardization entities like ISO or NIST that have also been working on this. And in particular, within the EU, there are at least 2 big projects that concern sort of this theme, which are the Digital Identity Project and the Digital Currency. But I want to give you another example, because we've been thinking a lot in this course, in this class, about encryption. Le calcul sécurisé, it's a lot about encrypting and how to perform things on encryption, and I wanted to put an emphasis also on authentication and how this can be really amassed in some cases. In the case of Signal, like groups like Signal, the way that you generally keep state is that you have a database, and the database has a record for each group, and each group has information like the title, the description, the picture, and the different roles that a person has, whether they're a creator or not. And clients can query the database, and one of the first things that we would like to do as cryptographers with this is like encrypt it. This seems pretty straightforward. We know of tools that allow us to like perform these operations, but the problem is that now you need to enforce access control and basic group management. But how are you going to do it if the data is encrypted, if you don't know who is a member? And so the way in which Signal does it is that by relying on zero-knowledge proofs, Alice can, for instance, contact a server and say, look, I am part of this group, my encryption is in the list of members, and I would like to add another member. Then another member, Frank, comes in, and they can still prove that they are part of the group with a zero-knowledge proof, and that they want to read the content of the group and decrypt it. Now, because the server does not know the encryption key, they are not able to know who is a member, like they're not able to tell what's the content of the group. And because Alice, by virtue of zero knowledge, is not revealing any information about the secret key, they are still able to perform operations while the server is able to enforce access control rules without knowing the secret key. The case of Signal, it's actually a very interesting sub-case of the case of anonymous credentials that I gave, in that we're not talking to different servers. I'm not like checking in and then badging in a door. I'm talking always to the same person, which is a subset of these anonymous credentials called keyed verification credentials, where I always am talking to the same server. These are self-contained systems where I want to perform operations, and I always go back to the same person while wanting to maintain anonymity. And I think it's actually one of the largest use cases where it's like really easy to deploy because it involves a single entity, but it's also the case that's used in Tor, that's the case that's used in Signal, that's the case that's used in some VPN providers, and so on. The recipe, the way in which we build all of these systems is simple. I need to make a zero-knowledge proof of a signature. That's all there is. So at issuance, I will get a signature, and then at presentation, I will give a cryptographic proof that I know a signature that verifies. The desire here, the way in which we have been building these systems for the last, I would say, more than 10 years, is that there is some desire of compatibility. We want the proof system not only to support the verification equation, to be expressive enough that it can express the verification equation of the signature. We want them to talk the same algebra. We will like the cryptographic proof system, you know, that, for instance, works over circuits over finite fields, to speak to be essentially the arithmetic that the signature scheme needs to do. And this is where a lot of mix and match has been done in order to build efficient systems. And once you have these two core systems, you will like the cryptographic proof to prove something else about this hidden value, which is what gives you, at the end, an access policy. And in the case of keyed verification system, you don't even need the signature. All you need is a MAC. You need why? Because message authentication codes are essentially signatures that are secret key, where I'm always using the same key for signing and verifying, because I'm going back to the same person. And so we can make this really efficient. And the blueprint for doing this is that, you take a signature scheme. What are the properties of a signature scheme? Correctness and unforgeability against chosen message attack. It is not possible to make a signature for a message that I did not sign. From it, you would take a zero-knowledge proof and try to see if the zero-knowledge proof can support the verification of the signature. What does it mean? It means that I want to prove that I know, well, let me, I want to, there is a typo in the slide, but it will be corrected in the next one. I want to prove that I know a message and a signature that is valid under the verification key. That's all that I need to prove. After that, generally I want to build a credential system where some of the attributes are hidden. One of the things that's useful is when I want to do certificate delegation. I want the user then to be able to sign other things. Or I want the user to have some private personal attributes that the certificate entity does not want to reveal. In this case, it's useful not to think about like signing a message, but rather signing a commitment. If you don't know what a commitment scheme is, think about an encryption. I want to sign an encrypted value and prove things about these encrypted values, some parts of it. And then during the representation phase, I will want to check whether they satisfy the verification equation of the signature and the commitment is valid. On it, I will be able to, maybe pick some other predicates, what are the properties that this signed message needs to satisfy so that I can enforce an access policy. Is this person trying to access the room number that they have been attributed to? Is this user allowed, do they have enough credit to perform this action? This is the sort of things that we check with access policies. And informally, if you're able to break the access policy, then what could have happened? Well, either the zero-knowledge proof was not sound because you proved a statement that was false, or maybe the proof system was right, but you broke the commitment scheme because you found another message that was valid. Or you signed the correct, or you committed to the right value, but you signed the wrong message. And so there is this stack of security properties that we can do to carry out a reduction and prove mathematically that the access policy must be really satisfied. Informally, the security will rely on soundness of the zero-knowledge proof system, the binding property of the commitment scheme, and the enforgeability property of the signature scheme. There are lots of access policies that I could spend the entire day talking about them. The ones that I would like to emphasize, like some simple ones, is that, for instance, you can have public metadata on these attributes. You can say, these attributes logged in or was given a credential at this specific date. I can set an expiry by providing a range proof, by saying, whenever I give a signature, I can prove to you that this signature is fresh enough. And we saw just earlier how you can make range proofs, and this is really within the framework that we saw just before. Another thing that you can do is build pseudonymous identities. So an identity that can be generated from this credential that is valid and that is different for every different namespace that I'm accessing. Imagine getting rid of cookies and being able to have an identities without having to register on each website by creating an identity that can be trusted and that is different on each server, and the server cannot tell, servers colluding cannot tell if they are the same person or not. And that's actually the one that I would like to focus on. And, but another one is you can do access control. A lot of access control today on the internet is done by, you look at the IP address, what is the GeoIP? Did I get a lot of requests from this guy? Do they have a cookie set? And all of these access control policies are really harmful for some users and do not necessarily provide the right solution for the problem. In that a lot of users use VPNs, a lot of users are in collective Wi-Fis and are making a lot of requests. So these tools are sort of a toolbox that can be also used in these cases online. And as an example, I wanted to give you an idea of how can you build this system, essentially using what we saw so far. And so again, the problem here is that we have a user. The user wants to create multiple identities, and they are all the same user, but to the view of the server, they are not. And the only component that we need for this is something that is well known to cryptographers, that is a PRF. If you don't know what is a PRF, think about a hash function. There are two properties here. It's a function, so they can be efficiently computed. And if you don't know the key to this keyed hash, you cannot distinguish from a uniform distribution. What we can say is that this distribution can be simulated without knowing the secret key. But one such example that is algebraic and can be done in the framework of Maurer and Sigma protocols is NPR, where the key of the hash function is a scalar, and the message is hashed into the group, into a group element of which I do not know the discrete logarithm of. Now, the output of the hash function is a group element, and I can give you a lot of messages, but all of them are indistinguishable by virtue of Diffie-Hellman. I'm using the same discrete logarithm for all of these group elements, and I cannot tell which one it is unless I'm able to distinguish Diffie-Hellman triplets. And so what you can imagine is a system where the server gives you is issuing a signature for a secret key. And we know how to build the signature just using groups, and we know also how to commit to elements just using discrete logarithm and groups. And whenever the user wants to present a credential, when the user wants to log in at a specific URL, what they would do is that they would evaluate the PRF at the given URL, and they prove validity of this. What does it mean? It means proving that they know a signature for this secret key, for this PRF key, or better, a commitment to it, so that the commitment opens to it, and that the PRF has been correctly executed. And now if you think about this statement, that the PRF has been correctly executed in the example that I just gave, this is really about proving pretty much a Chom-Pedersen relation. Just proving that I know a secret key that multiplied by these group elements give me this other group element. And you know, I can do this over and over again. And because the zero-knowledge proof is, well, zero knowledge, all this data that I'm sending does not reveal any more information than the names are computed correctly. And because the PRF is, well, a PRF, it is pseudo-random. So all these are random strings that I'm sending. And I can still enforce access control with these because the PRF is a function. I cannot just produce as many output as I want. I cannot create many fake identity. I cannot mount Sybil attacks in these. And also the zero-knowledge proof is sound, so you cannot produce false statements. And finally, the signature scheme is unforgeable, so you cannot create fake. You cannot forge proofs. You cannot create new identities without knowing the signing key. Okay, so close this parenthesis. I wanted to give one last example around anonymous payments and how, again, they can be built using the tools that we saw so far and maybe like give an idea of like what's the state of art in this area. I wanted to start like instead of going full crypto bro and blockchain, like maybe start with more concrete examples here. And you know, I did my PhD in a school that, like most French schools, has these sort of machines where you know, you have your student card, you go there, you top it up, and then you know, you get the credit, and then the credit can be spent. This is essentially an anonymous payment. Sorry, it's not anonymous. It's a payment mechanism. And you know, you can see like down there on the right, there is this little wire, and this wire goes up to a database. And the way in which the user performs actions using this machine is by, you know, building a transaction. And this is no different from what we do online. And this transaction essentially has data like, you know, the date where this transaction has happened, what is the time when the transaction was done, what is the username, who is making the payment, who is topping up their account for using it later, and what's the amount that's being charged on the card. And, you know, these transactions are things that go in a database that then will record this account has this much money. And ideally, you want these transactions to be authenticated by the machine. And you know, what is the primitive that allows you authentication? Well, it is definitely not error correcting codes. Error correcting codes will provide you integrity, will say like this data has been transferred correctly. And so what you really want to prevent is an adversary that could, for instance, you know, plug a script and alter the transaction, for instance, the transaction amount, into a higher value and recompute the ACC. Again, the primitive here is a signature scheme. You want to perform some authentication of the values that are being transferred. What we know and what's the state of art in this is that Zero knowledge proof can be used not only to authenticate payments, but also to hide the username and the amount while maintaining soundness of the system. It is literally possible to have a ledger that does not have any idea about who is in the system or how much money is in the system or who is making payment to who, except for the total amount of money in the system and knowing that this amount of money that's total is being kept there, is not being inflated. Transactions in Bitcoin are not much different from what we just saw. In Bitcoin, at some point, you need to create transactions. And that's exactly what we saw earlier. These are minting transactions, where you have an output, and the output is generating some value, V, and this output is associated to some username, which in a cryptographic setting would be a public key. Why do we need cryptography here? Because I don't want to steal the money of another user, which is what I could in the previous system. And from this, you can spend money. And the way to spend money is that you specify in the output list the recipient of the money, how much value is given to which public key. And then at the end, you would sign the transaction with a public key that has enough value. The property that you need of this transaction is that the transaction needs to be balanced. That is, the sum of the values in the output needs to be equal to the sum of the values in the input, to the credit that's being attributed to each public key. That is the way in which double spending is avoided. And, from this you can go on and on, build other transactions using signatures, not necessarily only one, as many as you want, that are previously unspent outputs. These are like public keys that have some value associated to them. So what you end up with is like the state of the ledger, the state of the system, is essentially a list of public keys and of values, and these are like values that have not yet been spent. These are unspent transaction outputs. The way in which a cryptographer will look at this is like, well, you're saying a lot of information here. There are public keys and there are values. That is also why we say that Bitcoin is pseudonymous, because everyone has a public key here, and we're trying to get rid of it. And first of all, you might want to hide the amount, and a trivial solution here would be, well, instead of having the value, how about we commit to them, we encrypt them in a way. And we know of commitments like Pedersen commitment that can do the job easily. And in fact, they are not only do the job quite easily, they are perfectly hiding, which means literally no information about the value is revealed, but I cannot change my mind about the value later. And now, I can think about, okay, so I replace this value with this commitment, but how am I going to check that the transaction is valid? Now the value is hidden. I cannot really check whether the sum of the outputs is equal to the sum of the inputs. And the way to do so is by noting that Pedersen commitment are playing some algebra and they are homomorphic. So the sum of the commitments is the sum of the committed values. So if I take the sum of the outputs minus the sum of the inputs, if the transaction is balanced, I end up with a commitment to 0. I end up with a commitment to the 0 element, modulo P. And what you can say is that, well, if this is a commitment to 0, then I can think about this as a secret key, and as a public key called the XSE, and I can put the signing key as a sort of a way of demonstrating that I really know the opening of this commitment. This is really a commitment to 0. But all of this is still true only if the sum of the values is equal to 0 modulo P, not in general. And when I'm playing with finance and accounting, I'm not playing modulo P, I'm playing over the integer. So what you need to do is you need a zero knowledge proof that also tells that the value is small enough, that there is no arithmetic overflow happening. And what was sort of at least one very interesting thing that I learned while studying these sort of systems is that once you have these zero knowledge proofs that sort of prove I know an opening for this commitment that is small, there is no integer overflow, you don't even need to think about secret key, signing keys and public keys anymore. You just need to think about commitment and openings. So there is a coin, this coin has some secret opening, and I can spend it as long as I know the opening. there is no notion of public keys, there is no notion of identity. There are only values, coins with secret keys that can be spent. And knowledge of this opening whenever I build a transaction is sufficient for security. This is something like crazy. You can literally just commit and encrypt values, and then with zero-knowledge proof, you can prove that the transactions are being done correctly. And so what you end up with is, at least in theory, a system where you can build these transactions that have, again, a list of inputs and outputs. And the inputs, in the case of a minting transaction, in transactions that are being built, are public values, are commitments of which the randomness is always known. And the outputs are essentially saying, this is the commitment that I want to bring it to. And the signature at the end is just saying, I know the opening of this commitment under this excess, which is, again, the sum of the outputs minus the inputs. And whenever you want to spend a coin, you would build the list of outputs, which is the set of maybe change coins, but also the money that you want to send to the recipient. And then in the input, you would put the commitment that, a reference at least to the commitment that was previously appearing as a spent output. And so you end up in a system that has a lot of these transactions, and these transactions have only like commitments and signatures and range proofs. And what you can say, one of the things that's also fascinating about these systems is that these transactions can be aggregated together in order to provide even more anonymity. You can consider, in fact, a joint transaction, the sum of these two transactions, that is just the concatenation of the inputs and the outputs. Take the inputs from one, put the other inputs. I put the outputs of one, and I put the outputs of the other. And now the transaction is balanced if the sum of the inputs is equal to the sum of the outputs. And, it just works because that by virtue of concatenation. And the only thing that I need to drag are like these public keys, these excess signatures that I have for each single transaction. What's even more interesting in this example is that even though all the values are encrypted, outputs that reappear as input can be eliminated. So if Alice sends some money to Bob and Bob sends some money to Charlie, it will first appear as output and then it would appear as input. And I can just remove it because they don't contribute to the final sum. And so the trace that Bob got the money at some point only stays in this value E and in the signature that I have. And, sums are commutative, so I can even shuffle this list and destroy the link between the individual transactions. Again, modulo these signatures in here. And so you end up with a ledger. The state of the system at this point is just like the concatenation of these transactions, eliminating the inputs that reappear as outputs. And because we always start from minting transaction, the ledger, the state of a blockchain is essentially outputs that are unspent, where I know the state of the system, and I have sort of like authentication tags attached to it. Now, all of these can be built using range proofs, which can be built pretty much using only Sigma protocols with our composition or in the malware framework, and homomorphic commitments. And so it's a really simple system that allows to achieve a reasonable amount of anonymity. What is the level of anonymity here? It's that the values are hidden, and within a transaction, you cannot really tell who is sending money to who. But there are many types of anonymity that you can get, and most modern privacy-preserving coins have a way of not having anonymity within a transaction, but having anonymity within the unspent transaction output. And the way to do it is by saying, I'm taking one element from the transaction output, and I'm burning it. And burning it means I'm revealing a PRF evaluation of it over a message, and then I'm creating new coins that I'm putting there. So the anonymity set can be different. In this case, it's only for transactions, but it can be as big as the entire unspent transaction output in the entire history. And okay, so wrapping up, I wanted to give an example of what proofs are. There are many different definitions of proofs. Proof, I think, at this point are more like a process than an actual simple thing. We saw how you can do authentication while preserving some notion of anonymity, and some transactions. I'm here if you have questions. I also wanted to give like another resource that my advisor recently published, that's Snarksbooks, that talks mostly about how to base all this framework of zero-knowledge proof only from hash functions. And so while here we've been focusing a lot on like public key cryptography, which allows to build very simple systems, there is an entire line of literature that I hadn't had time to explain that thinks mostly about hash functions and how you can build efficient zero-knowledge proofs from them. Thanks.